interruption. 莱文斯、
叶老师，
加拉兹
Here.
，OK，伊丽莎、
Here.
汉飞然、
Here.
汉飞然 ，OK，萨贝斯、
Here 老师。
马奈、马奈
Here.
，OK，西部落
Present.
，OK，莫南加 ，Not here，山卓星 ，No，苏拉扎
Here.
，OK。So I like to check whether if you don't have microphone, and then please type the text over here to let me know that you are in the online in the Google Meet room. Okay, thank you. And another thing is that since I'm not not easy to connect your English name to your Chinese name. So if is convenient for you, please write down your student number as well, so that I won't misunderstand who you are. Sorry, I got COVID last Friday till now, so I have to lecture online to avoid somebody is, let me check. $202. Okay, wait a minute. Elisa, okay. Last time we talked about the diffusion, so we will go on talking about diffusion as well. If you have any question, I like to look how somebody. Who is the one just entered? Okay, nobody tell me. So please use this one.
204 老师。
Huh?
204.
204? Okay. $204, 克莱德, right?
Yes, 老师。
Okay.
201. Also put in the chat there here.
Balaya. Okay. So here you can find a hand sign over here. And if you want to ask question, just click this. I will, there is a sound, ring. And then if you are not sure that I listened, I heard that, and then click multiple times. Okay, so that I will notice that someone would like to ask questions. Feel free to ask if you have any question when I lectured. Okay, you can interrupt me, no problem. I won't feel angry. Okay, so Uh, I think this is the first time for me to lecture online to your class. I will tell you about how to use the Google Meet. And during the pandemic, in fact, we had a lot of online classes before. So I'm very used to use the online facilities. Uh, but I'm not pretty sure that you are familiar with that or not. So if you have any question, just click this one and let me know, and I will have you say something and answer your question or worries. Mm, so, okay, so let's see, where were we last time? I think it's here, the non-steady state diffusion, right? Mm, by the way, I like to know that whether uh, you have any question about the steady state diffusion or not, or not review that not start reviewing. Okay, no matter what, let's discuss uh, about the non-steady state diffusion. For example, if there is uh, an aluminum bar and we have copper on one end, and of course there might be some initial concentration of the aluminum of the copper in the aluminum bar. So we have C0. C0 is the initial concentration of the copper in the aluminum, and at the time equals to 0, which means that at the start point time, start of time, and the concentration of this end, and the x position, x axis is the position underneath the aluminum bar, and y is the concentration of the copper, uh, concentration distribution, I should say, along the depth direction. So at time 0, we have CS. CS is the surface concentration, or we may say the source concentration. And at time 0, at this interface, uh, it is CS over here. And inside the aluminum bar, since the diffusion hasn't started, uh, so is C0. This red, uh, wait a minute. This red curve represents the initial distribution. And then at a certain time, T1, and is concentration distribution was something like this, which is from this one, and then a little bit like this, a little bit like this, and T2, T3, T4. Of course, uh, this direction, T3 greater than T2 and T2 is greater than T1. And if the time is infinity, and then we will have the concentration of the here, which means that all the aluminum bar, all the concentration of copper inside the aluminum bar will be identical to the source or the surface concentration. And of course, as I told you, it is impossible for us to wait for so long, and so we will stop at a certain time point. And how to stop it? I mean that how to know that when we have to stop, because it is impossible to wait for t equal to infinity. Generally, is something like this. We have a certain, we have another uh, actual mm, mm, concentration point at a certain depth, which means that, for example, we will set that at a certain time t3. Uh, may Of course we will find the problem will ask you to find the time t3, and we will have a certain concentration of C at a specified depth x, and please find t3. And that is what the problem will ask you. Okay, so we have some condition to solve the what we called the diffusion equation previously, and we have an initial condition which is at time equals to 0. We have the concentration of the source. Uh, Sorry, I should say that at time equal to 0, we have a concentration of C0 inside the element bar, which is the initial concentration. And at time at the boundary x equals to x0, and the concentration is the CS. It is also one of the boundary concentration. And so no matter, in fact, it should be said as no matter when the time is at this boundary, the concentration will always be CS, the surface concentration of copper. So there are two two boundary condition over here, and first is the concentration equal to CS at the interface, at the side, one side which is CS. So C equal to CS, the concentration distribution curve C will be equal to CS for x equals to 0. And another one is that if the bar is infinite, and then another boundary condition is that C equals to C0, and then we assume that this is a semi-infinite bar. The meaning of semi-infinite is that it has only one end, but with no other end, no other end at the other end. I mean that it can be infinite in this direction. If Of course this is an ideal condition, but however, in order to solve the so-called the diffusion equation, this is as I told you last time, this is a second order non-linear partial differential equation. and we have one order in time and two order in the location x or y. Here we have only x, uh, second order, and so we must have some two boundary conditions for the location. Otherwise, we cannot solve the partial differential equation. So this is the other one. Assume this is semi. This is a semi-infinite aluminum bar. So at this infinite end, and the concentration will be zero, which means that the diffusion will be go on and will be decreasing to zero at infinite point. This is another boundary conditions for that. Probably you will you will think that it is hard to understand about what I said. I can understand. I can understand your worry because uh, it's not very easy. It's uh it's an engineering math problem and advanced, I should say, advanced engineering math problem. So if you don't know too much about what I was saying, and it's fine because you don't have to solve the equation. We have the solution already. So don't worry about that. And and the solution for the for the non-steady state uh, diffusion problem, for this one, fix second law and partial C over partial T equals to a diffusion parameters times partial square C over partial X square. If you don't know too much about how to solve this diffusion equation, and feel free because you don't have to. And here we have the solution directly. All you have to do is how to utilize this to solve uh, the problem, the non-steady state problem. So you don't worry about how to solve this question. I won't ask you any question in the final about please solve the diffusion equation, something like that. No. Okay, let's see here. The solution is that CXT. What is that? This is, as I said, this might be the question that during the test will ask you. I will ask you, and because this is a condition about a heat treatment condition, I should say. And CXT is the concentration at point X, a certain depth X, at a certain time T, and I will specify the concentration for you, and I tell you the position. For example, the position is here, and the concentration already known here, and I like you to find out the time T, or I tell you the time T and the depth X, and please find out C at that specified point and specified time duration. This is C. This is the meaning of CXT minus C0. C0 is the initial. Sorry, yes, initial copper concentration inside the aluminum bar over C surface or source concentration minus C0, the same, the initial concentration in the aluminum bar. equals to 1 minus error function ERF of error function of x over x is the huh? Okay. I thought there would be something written here. X is the location specified over 2 root dt. D is the diffusion coefficient, like here, this one, the D. Root dt, t is the time duration. Okay, this is the answer to the unsteady state uh, diffusion question. Now, I know that you will ask, you will have a question would like that you like to ask. What is error function Z? Of course, Z stands for all these stuff. Error function. Error function. The definition of the error function as if it's written as error function of Z. The definition is that the error function Z equals to 2 over root. Wait a minute. Uh, Integration from 0 to Z exponential minus y square dy. As you can see, this is a very I won't say it's a very complex function, but however, it's not simple, right? And but fortunately, you have error function value given in table in your textbook because table 6.1 is for the blisters version. So if you are for the escalant is 5.3 in your textbook. Sorry, because I'm at home and I do not have bring the textbook with me to home, so I can't show you about where it is. But I think you can find that you can find table 5.3 by yourself if you have your book with you right now. Okay, so you can find there will be two in this error function table. One line is the error function of Z. Another line is the value of error function of Z. You may think error function of Z as the y, which is y equals to f of x, and Z is the x. So you will have one column of the variable and one column of y, the value of error function over there. And you can once you calculate, you get the value of x over 2 root dt, which is the z over here. Once you get the value of this one, and then you can find out the value of error function from table 5.3, and then insert the value to here, and uh, you can find out the value of 1 minus the error function value, and then on the left hand side probably it is the concentration that you are interested in, and then you finish calculating all the others and then solve C of xt from this equation. That's how to find the concentration at a certain point x and a certain time t. Is there any question about that? Okay, so I think you must be overwhelmed about what I said. And so let's have a simple problem about what I said. A non-steady state diffusion question and face-centered cubic carbon alloy initially containing 0.2 weight percent of carbon. Okay, here I like to explain you about weight percent here. In fact, I told you before what's the meaning of weight percent, right? We have weight percent, volume percent, or atom percent, atomic, I should say. Of course, in short, atom percent uh, of some elements. And here, WT percent means it is the percentage in weight, which means that carbon, the percentage of weight for example, 100 gram, and the carbon takes 0.2 gram. This is the meaning of weight percentage. Okay, and of course we have volumetric, or in short, volume percent, volumetric percentage. And for this sample problem, we specify the heat treatment temperature, the time, the source concentration, and the initial concentration, and we would like you to get the concentration at a certain or specified depth. This is what the problem would like you to obtain. Okay, so let's go on describing this problem. So we have an initial concentration of 0.2 weight percent of carbon in an FCC iron carbon alloy. Okay, and this block, this alloy, is going to be copperized, and so it's copperized at an elevated temperature and in an atmosphere that gives a surface carbon concentration constant at 1.0, constant at 1.0 weight percent, which means that this is the surface or the source concentration, which means that if it's here, and which means that this bar at this end is exposed to a carbon-rich condition of 1 weight percent of carbon. Okay, so now the heat treatment starts, and after 49.5 hours, this is the time t, specified time t. And after 49.5 hours, the concentration of carbon is 0.35 weight percent at a position of 4.0 millimeter below the surface. Okay, so we have the depth, sorry, the depth 4.0 millimeter over here. And we have the final concentration, CS, sorry, not CS, C of XT. Sorry, this over here, it is not to get the concentration at specified depth. it is going to ask you to find the temperature. So we have C here, we have X, we have T, and we have the CS. Wait a moment. Sorry. So you can see here that in this solution, we have the concentration distribution C, which is 0.35 here. And we have C0, which is 0.2. And we have, we have CS, which is 1. And we have X and T, which is X 4 millimeter, T 49.5 hours. Please watch out. One thing, very important, please write it down. By the way, today you still have to upload your notes as well, although it's online. Okay, remember, each uploading you can get at most 2 points. So don't lose your right to get extra points. Okay, so we have almost everything for this except for time t. Sorry, not for time t, except for the temperature. The temperature is not shown here. Maybe you will think that teacher, and then what's the role for the temperature in this solution? Okay, you can see here that now we still have an unknown over here, right? The D. D, the diffusion coefficient or diffusion parameters, is directly related to the temperature. As I showed you before, the higher the temperature, and then the greater the D will be. And even only maybe 50 degrees C of temperature difference, D may be multiple of maybe 2 times or 3 times or even 10 times greater. So D is directly related to the temperature. So now we start to solve the equation from the fixed second law. And as I said, the only unknown is the D. So we have this. Please watch out. Now we are using 49.5 hours. And as I said, please watch out very, very carefully. And because when calculating, we have to change or convert hours to seconds. Please watch out, because we have to make all the units to be consistent. So we have all these known conditions, and then we start to solve the equation over here. And now we have everything over here, because we have the specified concentration at a specified location, and the time, which is 0.35. This is a known condition from here. So 0.35 minus the initial concentration inside the iron, and source concentration minus the initial concentration. So we know all the values over here, and 1 minus error function of this one. Since we don't know D, so we cannot calculate all these, although we know X and T, because we don't know D. So assume that this is an unknown. So it's 1 over error function of D. But however, since we know this one, so we may have a look at the table. In your table is the table 5.3. Okay, as I showed you here, table 5.3. So we have error function of D, which is equal to 0.8125. And then we like to find out D according to the value of error function of D equal to 0.8125. So how to get the 0.8125 of error function value, and how to get Z out from the error function of this one. Okay, let's have a look about this one. This is called interpolation. interpolation, interpolation. And this one. My cursor is not smooth. Okay, this one, interpolation. What's wrong with it? This one. Okay. And to find out that, let's have a look about the table. In the table, probably you cannot find a direct value of D, error function of D, which is 0.8125, and calculated from here. Maybe, or very, very probable that you cannot find this. So all you have is that when error function of D equals to 0.7970, and you have D equals to 0.95, and error function of D equals to 0.8209, and the D value is 0.95, which means that first step, we have to find out two error function value, which is one is greater than the specified value 0.8125, and the other one is smaller than this one. Sorry, greater than this one. And then with this one smaller than this one greater than this, and we can assume, or we can know that the Z must be between 0.9 to 0.95, right? So assume that the variation from 0.797 to 0.8209, and assume that the change from here to here, and the change from 0.9 to 0.95, the change either for X or for error function of D, or error function of D, are linearly proportional. And then we can use the so-called interpolation method. Here, the principle of of the interpolation we can find out from this one. Assume this is D1 0.9, D2 0.95, and error function of D. Error function of D1 is 0.797. The error function of D2 is 0.8209. And then if we draw two lines, for example, like a triangle over here, and we have D1 here, D2 here, and we have error function of D1 here, error function of D2 here. As what I said, if they are linearly proportional, if we draw a line from, assume this is A prime, A double prime, and this point is B prime, B double prime. If they are linearly proportional, and then AB will be parallel to the okay, here D is this one, and error function of D1, sorry, it should be D. Please do not, this is not D1, this is D, error function of D, which is Y is 0.81225. Please watch out, formerly I wrote this wrong. This is error function of D. Okay, and so AB, line AB is parallel to line A prime B prime, and is parallel to A double prime B double prime, which means that these three lines are mutually parallel. And then from since they are parallel, so the ratio of A prime to A double prime has to be the same with the ratio of B prime to B double prime, the length of the line segment. I mean the ratio of the line segment A prime to A double prime should be equal to the ratio of line segment B prime to B double prime. Okay, this is what the the interpolation. I mean the principle of the interpolation is. So with this, if this is a triangle, so we have OA to OA double prime equals to OB to OB double prime, or OA to OA prime, sorry, equals to OB to OB prime, which is this, if they are parallel each other. Okay, so since we have the value of D already, sorry, we have the value of error function of D already, right? So OB over OB prime or OB over OB double prime are known. So here, as I said, this line segment, the ratio of the line segment AA prime equals to to AA double prime equals to BB prime to BB double prime. So we have this. So we subtract, for example, BB double prime, which is error function D minus error function of D1, to air function of D2 to minus air function of D1, which is this one, has to be equal to this one. D minus D1, D2 minus D1. Okay, on the left side, it is this one, the ratio of the line segment AA prime to AA double prime, which is this one. And the ratio of line segment BB prime to BB double prime is this one. And then we know we know all the values except for Z, right? So the only unknown for this one is Z. So we have this one here. This is from here. So we have Z minus 0.9 over 0.95 minus 0.9 equals to 0.8125 minus 0.7970 over 0.8209, which is this one, minus 0.7970. Okay, so the only unknown here is the Z. So we can get the value of Z, which is Z equals to 0.93. Okay, so over here, if you don't know the interpolation before, a little bit harder for you. So practice yourself. Practice yourself how to obtain the value from the interpolation. Okay. So, but however, if you knew it already, sorry, maybe it will be so boring. Is listening to what I explained. Okay. So we can get the value is approximately 0.93. Of course, if you want more, more precise value. Okay, so you can, for example, maybe is 0.931 or something. Okay, so assume that this is 0.93 and this is precise enough. And then, sorry, someone. And then you will get your your Z value equal to 0.93. And as I said, D equals to this stuff, x over 2 root dt. And D is the diffusion coefficient. And then with some arithmetic manipulation, we can find out that D equals to this one. And we substitute Z with 0.93, and X and T are known value. And we can get, sorry, a little bit confusing over here. So we insert all the known value on the right hand side, and we can get D equals to 2.6 times 10 to minus 11 meters per second. Please watch out here. It converts hours to seconds over here, which means that 49.5 hours times 3,600 seconds, because 1 hour equal to 3,600 seconds. So you, as I said, you have to convert the hours to seconds to get the correct value over here. And it's not finished because the problem asking you is the temperature. It's not the diffusion coefficient. If the problem asked is the diffusion coefficient D, and then it's solved. But now it's not yet because we haven't found out the temperature so far. All we have is the diffusion coefficient D is being solved. So we have to solve the temperature, capital D. And with the Arrhenius equation, okay, maybe you don't know what this is. Okay, let's start from this one. This is the Arrhenius equation, remember? Uh, is something. Oh, Arrhenius equation. I explained to you last time, remember? And in fact, over there, that time I introduced you about this already. And so with the use of Arrhenius equation, and we will solve the temperature, capital T. Okay, so let's see how to do it. And to find out the diffusion coefficient from the Arrhenius equation, it is D equals to D0 exponential minus QD over RT, right? And then we take log on both sides, natural log, ln. And so we have log D equals to log D0 plus log exponential minus QD over R. In fact, the process for deriving the solution, I explained to you already, but I like to tell you one more time. And so this is log D0, and log exponential canceled out each other. So we have log this equals to log D0 minus QD over R T 1 over T. And so we move everything to the other side, only leaving 1 over T over here. So we have 1 over T equals to R over QD. QD is the activation energy, which is QD, R over QD times log D0 minus log D, and which is this one. And here we take reciprocals on both sides, so we have this one. So that is what this is. Okay, so T equals to QD over R times 1 over log D0 minus log D, which is this one. Okay, this is how to derive this. And when this is known, of course, we have D over here calculated from here. So we have D over here, and D0 QD can be found from the textbook. I told you which table it is, right? Since I don't have the textbook at home, so please find it out yourselves, and then from the table. Fortunately, it's here. Table 5.1 from the Escalent textbook. And you can find out the time T. because the diffusion of carbon in FCC iron, which is the gamma iron. And so we have D0 and QD found here. And then substitute these two into here, because R is the universal gas constant, 8.314. And with D0 and QD found out and D calculated from the previous page, and then substitute into here, we can find out the T, the time, the temperature T, which is approximately 1300 Kelvin in degree C, which is 1027 degrees C. This is the answer to the question. Relatively harder or complex uh, question, because you have to you have to solve T by two steps. One step is to find out the diffusion coefficient from the fixed second law, and another is to find out the temperature T from the Arrhenius equation. So relatively harder for maybe for all of you. And so please maybe is 10:15 already. So maybe I'll have a break for now, and so that you can maybe uh, to review something that I lectured already. But before doing so, I like to take the attendance again for those who aren't here. And Korean,
I'm here, 老师.
okay. And Diaker,
I'm here.
okay.莫兰家
Present.
，okay. 山卓星
Present.
okay. I think all the others are still online, right? So I don't want to waste too much time taking attendance for those who are here, who were here when I took the attendance first at the first time. So let's take a break. Now is 10:18, so we will have a 20 minutes break for all of you, and I think it's until 10:40. And so and then we won't have another break until 12 o'clock. Okay, we will have the second class, and the class will be finished around 12 o'clock. So 20 minutes of break from now. So let's take a break. Okay, let's go on. Hope all of you has returned to your seat. Okay, so let's go on. Another example. I think this example I told you before, but at that time is for the steady state diffusion, the chemical protected clothing (CPC), and methylene chloride uh, is a common ingredient. Blah blah blah. Okay, that's fine because I told you before at that time. No, yes, yes. Here, if the uh, butyl rubber glove 0.04 centimeters thick are used, what is the breakthrough time? And that is how long could the glove be used before the methylene chloride reach the hand? So here it is very important because don't expect that the rubber glove can isolate your hand from uh, being touched by the chemicals. Okay, so let's see here. We wanna find out the breakthrough time TB. So of course we have a given data because the data can be found easily. So in this question, it's given the diffusion coefficient for the rubber is D equals to 110 times 10 to minus 8 cm cube. Sorry, cm square per second. So now let's start solving this question and assume that this is a linear concentration gradient, and we want to find out the breakthrough time TB. And the TB here. Sorry, it is not listed because it's in other question over here. Assume this is a known equation. The breakthrough time equals to the L square over 6D. And D is the diffusion coefficient, 110 times 10 to 8. So L is x2 over minus x1, which is the thickness of the glove. And so the TB can be calculated with the data given. So it is approximately 4 minutes. So when you use the pen remover, I mean, to put your hand to being immersed by the pen remover, before 4 minutes, your hand is safe. After 4 minutes, the concentration of the pen remover can be penetrated. It can penetrate the glove and reach your skin. So the time required for breakthrough calculated is approximately 4 minutes. Okay, so I will. This is not the assignment for today. This is not today's. This is approximately 5 years ago. So I will assign the question in line group or in the uh, in the e-learning site, and I will give you two weeks to do the homework. Okay, so that finishes the chapter number 6, and let's go to chapter number 7, the mechanical properties. Mechanical properties of the materials. So here in this chapter, I will introduce you about first cursor is not moving very smoothly. Okay, first we will discuss about what is stress and what is strain, and second, elastic behavior, and then plastic behavior, and toughness and ductility. Okay, maybe you don't know too much about those terms. It's fine, because all the terminology I will explain to you during the class. First, let's see the elastic deformation of the material, and assume that this is nanoscopic or even atomic scopic point of view of the material. So let's see here. The circles represent atoms. So when it's being pulled with a small load, and you will see here that the distance between two different rows, it will be stretched a little bit, so the bounds stretched. and we will have, since the bar is pulled with a certain load, so there will be a deformation delta existed with due to the force F. So if the load is small enough and is purely elastic, so we will have a line like this. Assume that this is the deformation, this is the force, and we will have the force displacement curve, something like this, and the force the force is released, and then it will go back to the origin completely. Okay, so this is called elastic deformation. So the meaning of elastic means that it can be reversed, which means that it's reversible. So adding the force and releasing the force, and adding the force and releasing the force once again, and then it will follow the same path of this curve. This is called elastic deformation. And however, not it might be elastic, but it might not be so linear. Some material will go this way. This is called nonlinear elastic deformation. It deforms according to another nonlinear curve. And in this curve, you will see that the material will have an unevenly distributed deformation. However, it can return to the origin completely. It is also called elastic, but nonlinear. And in the materials, mechanics of material, I should say, and we will not consider about such material because it's not easy to anticipate their behavior. Okay, let's see about the plastic deformation. And generally, we will not have a pure plastic or pure elastic material in real world. So, what is the meaning of plastic deformation? Let's see here. Initially, it's also the same. The circles represent the atoms. So when it's pulled out, generally, the deformation contains two different elements. One is the elastic deformation. Another one is the plastic deformation, which is delta elastic plus delta plastic. And when the external force disappears, and then of course this bar will rebound back, but it will not go back to its original length. And actual deformation will, or actually we should call it a permanent deformation, will be left over here. This is called delta plastic. The meaning of plastic means that it will deform permanently. It won't rebound back completely. So in this case, you can see, unlike the previous one, when this rebounds back, and it will return to its initial position with no deformation left for the delta elastic part. But however, mostly, I mean, in real world, we have elastic and plastic deformation both. So we will have the permanent plastic deformation left. So plastic deformation means permanent. So if we observe the behavior from the force and deformation curve, so we can see something like this. When the force F applied, maybe it will go from here to here. Maybe initially it's purely plastic, but after all, it will experience an elastic plus plastic deformation curve like this. How can we know that? When we release the force, and then it will go back, not to the origin. Previously here, it will go back to the origin completely. But now, when we release the bar, and then it will go back to here, leaving a certain portion of permanent of displacement called the plastic deformation. Of course, it will bounce back a little, this length, because the final length is here, but it returns a little. So this portion is the displacement that it bounced back. So we call this here, this is the delta elastic. And here, this is delta plastic. And the total deformation, I mean, when the force applied, this is the delta plastic plus elastic, the total deformation over here, total deformation. So we have deformation, we have force. Now that I like to introduce you about a term, a special term. Probably if you are not graduated from engineering related, especially mechanical engineering related department, you haven't heard such term. Stress. Okay. The stress. What is the stress? Stress is the pressure inside the material experienced due to the force acting on it. This is called the stress. And we have tensile or tensile stress. We also have compressive stress as well. If it's a pulling force, and then the stress exerted due to the pulling force is called tensile stress on this material, this block. Okay, now as I said, we what I lectured just now, we have two terms: pressure and stress. And the difference between stress and pressure, please write it down, because it is a very important concept. Because when you graduate from university, when you go to work in the mechanical engineering related field, maybe the boss will ask you, please tell me what's the difference between stress and pressure. Okay, here is the difference. The main, of course, the difference might not be only 1 point. Sorry. But most of the case, we will define the pressure as the external force acting on an object. So if there's a force, no matter tensile or compressive force, and those forces acting on the surface of the material will have some kind of pressure or compression. I mean, maybe tensile pressure or compressive pressure on the material externally. So which means that the pressure, first, please watch out. Maybe you can write down by yourself, because so far now I'm at home. It's not easy for me to write it down. And maybe you will feel very interested about how can I write those words, because at that time I have a pad to write connected to the computer. So that is why I can do that. But for now, I cannot, because I don't have the pad in my home. So please write down by yourself. For the pressure, it is a superficial phenomenon, which means that the pressure can only uh, be occurred on the surface, which means that since it is the reaction of the material to the external force, so either the pressure, sorry, I should say that the pressure is only a phenomenon occurs on the surface only. And but so as you know that if I have a rubber, and then when I pull the rubber, there must be some kind of force acting in the interior of the rubber band, right? And of okay, so the force acting inside the material due to the external force, I mean the force inside the material, is called a stress. The stress. And if it's a tensile force, and then we have a tensile stress. And I mean that if it's a pulling force, and then we have tensile stress. If it's a compression, we have a compressive stress. Okay. So the stress is a pressure to counterstrike the external force. However, it is in the interior part of the material. So it is in an internal force to resist the external force. This is called the stress. So pressure is the force acting on the material. Stress is the pressure to resist to resist the external force, and it is the force or it is the pressure inside the material. However, the stress, when the pressure released, the stress will be disappeared immediately. So it is maybe like the Newton's third law. It is the force and reaction relationship. We have a pressure, and then we have stress. Because of that, and so the stress has the same unit as the pressure. So in BG unit, it is pound force, lbf. over inch square, or in SI unit is the Newton over meter square. This is for the stress, the unit of the stress. So how to calculate the stress? The same, and it is the force Ft over the area A0. And what's the meaning of you may call it A0 or AO. It's all fine as long as you know the meaning for that. AO is the original cross-sectional area before loading. What does that mean? It means that it is the area before the load is acting on it. And then you will ask, will the area change after the force acting on it? The answer is yes, it will. As you know that, for example, if there's a rubber and you stretch the rubber, you will see the rubber band will become thinner. Not okay. So the cross-sectional area will change. Usually or generally it will be smaller and smaller if the force is larger and larger. That is why we use the original area to calculate. Maybe you will think that, teacher, that seems to be not real, because in real world the area will change, not a constant. Yes, you're right. But so we will have another term called true stress. Here, please watch out. This is called engineering stress. The meaning of engineering stress is that it's simpler. If we assume that the area is a constant, and then sigma is also a constant throughout the calculation, it will not change. So it is easier. For engineering calculation, we want the calculation to be not very complicated. So that is why it's called engineering stress. So remember one thing, for the calculation of the engineering stress, the area is considered constant, the cross-sectional area. Okay. And we have tensile stress or compressive stress, and the line of action. The line of action is normal to the cross-section area A0. So if that is the case, and I mean, or is normal to the surface area that the force is acting. If that is the case, we called the force to be either tensile or compressive force, and which is normal to the surface or cross-sectional area, 90-degree normal to that surface. But it's not always so perfect, right? Because generally we have a force that is not exactly normal to the material, right? For example, if there's a block over here, and it is not always the case that you will act on the surface normally. And for example, if you want to pull it out, maybe you will use a little bit a force that is with some angle to the normal line. So if that is the case, because generally the force will act on the surface with a certain angle theta, and if that is the case, we can we can decompose the force into a vertical force and a tangential force, and which is Ft. T means tensile. Please watch out. T here, the T doesn't represent tangential. T means tensile. It's very easy to be confused. So please watch out. T means tensile force. Okay, and S is shear force. So we can decompose the force into a vertical component and tangential or horizontal component with respect to the surface. Okay, so for the Ft, we call it as the normal stress with the symbol of sigma, as lowercase sigma. Please watch out. In engineering calculation, we always use sigma to represent normal force. Please do not use other symbol, okay? Please do not, or even furthermore, we use tau to represent the shear stress, which is tangential to the surface. And we use tau to represent the shear stress. Please do not switch sigma with tau. Never. Of course, sometimes we have, for some tensor representation method, we will have sigma ij to represent either normal or tangential component. But however, if we do not deal with the question like that, please always use sigma to represent the normal stress, and tau to represent the tangential stress. Okay, inside this block. So tau is the shear stress exerted by the shear force Fs acting on the surface. So now you know the meaning or the difference between pressure and stress, and the two different stress, which is normal stress and shear stress. And no matter is normal stress, or we call it either tensile or compressive stress. No matter it is normal stress or shear stress, the unit will be in SI unit, Newton per meter square, or in BG unit, pound force per inch square. They are the same. I mean, they are the same in, they means both the pressure and the stress. They are the same in units. They have the same units. So stress and pressure have the same units, either Newton per meter square or pound force per inch square. The calculation for either the sigma or tau, we will use the original cross-sectional area instead of using the instantaneous area. As I said, the area will change with the value of the stress. Okay, so for simple tension case, what is the meaning of simple tension? And generally, we describe one thing that has obviously that has only simple tension, which is the cable, like the rope or some other or rope or cable. And because as we know that it is impossible to apply a compressive force on the cable, so only tensile force can be applied for the cable or rope. It cannot resist compressive force. So for cable or rope, they can be considered, or while calculating, you can use the simple tension consideration on this case. Okay, if that is the case, if A0 is the original cross-sectional area when unloaded, and then the stress can be calculated, sigma equals to F over A0. and sometimes we have a torsion on a bar. What is the meaning of torsion? Torsion is a form of shear force, which means that you can only twist force acting on it. And for example, here, this is the real to change the surface, the direction of the cable. For example, from here to the other direction, and in order to pull the cable, this shaft must have some twisting force acting on it so that it can pull this reel to turn. So generally, for any drive shaft, we must have torsion so that we can rotate, spin the shaft. In an engine, either the crankshaft or the camshaft, either crankshaft or camshaft, torsion must be acting. The acting force is from the piston and cylinder, mainly piston, because cylinder is the counterpart. The piston will transmit the compression force and to convert from the linear motion to the torsional motion to the crankshaft, and then drive the engine, drive the engine crankshaft, and so that it can transmit power to your wheel or your motor, I mean generator or some other components. Okay, so for torsion, you may think here how to calculate the torsion. You must have some kind of moment m. M represent moment, moment, moment. So you have a moment m, and rotating on a certain bar, and the radius of the bar is r, so the diameter is 2r. And then you can calculate the shear force acting on unit material, unit cube. So if the area is A0 and the force is Fs, and then you will have the shear force of Fs over A0, which is the tau. And then how to calculate tau? If we have a moment m acting on this bar, and we have a cross-sectional area or circumferential area AC, not cross-sectional. It's circumferential. It's like a ring shape area across or on the perimeter of the cylinder. We call it the circumferential area, AC. And if there is a moment M acting on the AC area, and let's see how to calculate that tau. And of course, the answer already given here. Tau equals to M over AC times R. And now let's see how to calculate that. And since we know that M, the moment, is the shear force times the arm, which means that assume there's a force acting on the surface, which is Fs. This assume that this is one unit surface area, and there's a shear force Fs acting on it, and assume that M, the moment, is known, and then we have M equals to R cross F, which is the torque due to the force acting on the circumferential area. So the R cross F which is the torque, and which is equal to the moment inside this material. And then R, as we know that is this capital R, and F is the Fs. So the shear force Fs equals to capital M, the moment divided by R, right? So we substitute this into here. In order to calculate tau, we substitute Fs to here, which is Ms over R over A0. A0 is the circumferential unit area, or circumferential area, total area, sorry, not unit. So Fs is M over R, calculated here. And A0 is the circumferential area, A0 or AC. And so tau equals to M over AC dot R. Okay, AC is a circumferential area. So, for example, if let me check whether I okay, you can see my image over here. And if this is a cup and AC is the whole side area, and the cross-section area is this, but AC is the surface area all around the side. This is called this is AC. Now, after explaining about the definition of tau and sigma, let's see some cases. Simple compression. And here we are discussing about some other common stress state. Simple compression. Generally in construction or building, mostly the condition we have is compression instead of tension. For example, if there's a rock over here, and the rock acting on the other rock beneath this rock, simply compression on it. Even for the RC or SRC, steel reinforced concrete case RC structure, and mostly for the concrete, it will sustain the compression force only. But for the RC structure, why it's not concrete only? In the building, we must add some steel in between the concrete. It's because the concrete can sustain compression very well, but it cannot sustain, or it cannot support tension. So when there are tension forces acting on the building, for example, earthquake, the earthquake will cause some kind of vibration, either vertical or horizontal vibration. The vibration contains both compression and tension. So when tension force is acting on the concrete structure, the structure will be broken, because in comparison to the compression force that the concrete can sustain, the tension force the concrete can sustain is relatively smaller, not just only a little, but very much. So to resist the vibration of the structure, we must add some concrete, steel, so that the steel can help sustain, resist the tension force. So for the SRC structure, steel reinforced concrete structure, steel is responsible for the tension, and concrete is responsible for the compression. This is why we use SRC structure quite a lot in civil engineering or in building. Okay, so this is simple compression case, and of course there are other common stress state, biaxial tension, and if they're for example, like this is a tank, as we know that either a gas tank or petroleum, either petroleum or methane gas. For gas tank, we may think of the tank as a thin shell device. So it has a very thin plate as the circumferential area. So if that is the case, only two axes on the shell surface are considered, because it cannot support or resist the tangential force, the compressive force acting on it. So for the shell itself, only sigma z, sigma. Should I say? Okay, let's see this here. Only this direction or this direction. The force acting on these two directions can be supported or resisted by the material. So this is called biaxial tension. There's another stress state called hydrostatic compression. And basically, for solid, it doesn't exist. I mean, for the hydrostatic compression, it will exist only in the liquid or gas state. What is the meaning of hydrostatic force or stress? Which is something, for example, the water pressure acting on a pressure vessel or fish. For example, if this is a submarine and the force the water force acting on the submarine or the fish, it is hydrostatic, which means that it is the same no matter the force is acting on from upward, downward, left, front or back, left or right, no matter which direction acting on this point in the water or in the gas, no matter how. To sum up, in the fluid, and then in each point, the pressure acting, no matter which direction it is acting on, they are the same. All the same. All these forces are the same, and the force, we call it the hydrostatic stress. And it is very important when calculating about the stress acting on the structure of the submarine or on certain vessel that will move under the water. Okay, so let's see here about the calculation. It's 11:30. About the calculation of the engineering stress and strain. So far, we explained it's about the stress. By the way, hydrostatic pressure. Sometimes we call it isotropic pressure as well. Remember, it only occurs in non-solid state, which is gas or liquid. For the solid, it will not. I mean that, for example, for the solid, the pressure acting on this direction, it will not be the same for the stress acting at this direction. Okay, so for the solid, it will not be the same for different direction. If the solid has the so-called hydrostatic stress state, and there is a special term for that. For example, sometimes you will have landslide, right? And it is because the water contains a lot of the soil contains a lot of water, maybe almost saturated. I mean water containing inside the soil. And then if that is the case, the soil will not be cannot be think as cannot be thought as the solid anymore. So when a force acting on top, the force will be transmitted to the perimeter direction, and then which cause a sliding or the force acting on the perimeter direction, and then causing the soil to move, which caused the so-called the landslide. So the special term is called the liquidation of the soil, and this is a very dangerous condition for the soil, because the soil will not be solid is cannot be thought as solid anymore, is liquidized, which means that hydrostatic compression might happen, which means that the force acting on top. Generally, for soil, it will not transmit to these four direction, only acting on top and acting on the bottom only. But however, if the soil has been liquidized, and then the force will be transmitted to the side, so therefore causing the sliding phenomenon. Okay, so engineering strengths. Now we come to the strain. for the for the engineering strain, and please watch out for the strain. We of course we think of stress. I mean that we may think of stress as pressure. If that is the case, we may think of the strain as deformation, right? Uh, Partially correct. Why? It is because for the deformation, the unit is in length, but for the strain, the unit is not in length. Is a ratio for the strain. So, for example, this might be the one of the unit used in strain, but mostly we will use this one. So the strain is a ratio, the ratio of elongation to the definition of the strain is the elongation, the ratio of elongation to its original length, which is delta, which is the displacement over the original length, L0. And let's see the dimension, the unit for delta, of course, is in length dimension, which is in SI unit, it is meter. And for L0, the original length, it is also in the unit of length, which is in SI unit, meter as well. So meter over meter, which cause the strain to be dimensionless. So watch out for the stress. It's not dimensionless. For the stress, it is in the unit of force, pressure. Sorry, pressure. And but for the strain, it is in the unit of meter per meter, which is dimensionless. But sometimes, because later on you will see that it is a very small value. For example, maybe 0.001 or something like this. Sometimes some will think that it is not, it is a little bit troublesome to write a lot of 0.00005 or something. So there is another unit, something like this. And please watch out, this is not a frequently used unit, but some will use the unit like this. It is millimeter per meter. What is the meaning for that? It is because generally for a meter long bar, the elongation due to external forces will be in the range of a few millimeters. So they will use this to save some time writing a lot of zero behind the decimal. So sometimes we will use millimeter per meter, which means that the meaning for that, this is millimeter of deformation per meter unit long material. This is the meaning for that. It's not a formal unit, but some will use that. So you have to know the meaning for that. And the this is the illustration for calculating the tensile strain. For example, the black circle, the black square is the original shape of the material when importing, and this material will deform something like this to become the green block. It will become thinner and longer, right? So you will have epsilon, which is the delta. Assume that the deformation, the total deformation, assume on each side it is delta over 2. Delta over 2. The total deformation is delta, and the original length is L0. And then we have the strain epsilon to be delta over L0. Okay, so this is for the normal strain, which is the strain in normal direction. But however, as you can see, in fact, we can also define a lateral strain, which is the deformation on the perimeter, on sides, and to the original length or width. We may call it width, W0. Generally, we will use the tensile strain instead of lateral, because for the lateral strain, we can see here that because when elongated, the block will become thinner. So we will have a negative elongation on the perimeter. Okay, so the definition, as I told you before, for engineers, we don't like a constant that is always negative. So we will add a minus sign over here to ensure that this value to be positive. So we have the definition of the lateral strain, which is minus delta L over the original width, and to represent the lateral strain due to the force acting on it. Okay, and this is tensile strain and lateral strain. And as I told you that we seldom use lateral strain. Generally, for normal strain, we will use epsilon a lot, but most of the case, sometimes we will use the shear strain to represent the strain caused by the shear force. So assume this is a block, and we have a force acting on this side in the direction of the red arrow here. And for this one, before the deformation, and this is the original block over here, we have 90 degrees on each corner. And after the deformation, the square will be deformed to this parallel pipette shape. it will become a little bit lower. But generally, we neglect the change in height, because generally for the material uh, under shear force, the deformation angle theta is small. This is kind of too much exaggerate, because most of the case theta will be only in 0 point something degree, or at least 1 or 2 degrees only. So it is not a lot, because if it deforms something like this so obvious, and the material already break down. So generally we will not have such a large deformation like this. But however, we will use this to tell you how to calculate the shear strain. As I said, for the strain, it is a ratio. And for the normal strain, it is a ratio between the deformation and the original length. And for the shear strain, it is the ratio of the original height to the deformation along the force direction. For example, here, the delta x. Assume this is x direction, this is y direction, and then the deformation along the force acting direction. And assume that the deformation is delta x, and the thickness is y. So we have the definition of shear strain, gamma. Please watch out. This is the usage for the shear strain. We generally we will use the Greek symbol gamma to represent the shear strain. We have epsilon to represent the normal strain. Okay, please do not use your own definition scheme. Okay, just use this, because this is the commonly used symbol. So gamma equals to this over this, the ratio of the deformation length along the force acting direction to the thickness of the block. So gamma is the delta x over x, the ratio of this one. And as we can see here, that if the theta is small, let's look at this triangle, and delta x over y, which is the definition of tangent theta, right? Of course, theta is in radian, not in degree. Okay, please watch out. And even more, if theta is very small, as I said, generally theta is not very large. It's approximately only 0 point something degree. In radian, it's even smaller, maybe 0.0 something. So because of that, in very small angle condition, under that condition, and then tangent theta can further be simplified as theta. And it can also be equal to sine theta if theta is very small, which means that the value of tangent theta is almost equal to theta or sine theta. So each value is fine, but strictly speaking is tangent theta. Okay, no matter what, all these three you can use without any problem, because for mechanics of materials, theta is very small. And lastly, in this slide, I like to tell you that again, to emphasize, the strain is always dimensionless, because it is always a ratio of the deformation to the original length, no matter it's in shear or in tensile strength, the strain. And here, to calculate, to test the shear or shear stress or shear strain, we have a device to test, and the name of the testing is called the stress strain testing, or sometimes we call it tensile test or universal test. And you can find the testing detail in an standard called ASTM, which stands for American Standardization of the Testings and Materials. And this, from my point of view, this is the most important material test in materials field. And we have 2 screws, and that is synchronized, and which can move the crosshead plate over here. And we have a load cell to record or to detect the force applied on the test bar over here. And we also have extensometer over here to measure the elongation on a specified length. This is a specimen, the test bar over here. And when we rotate the screw on both sides, and this plate will move horizontally, either downward or upward. If it moves downward, and then we can call it as a tensile test, because the specimen will be in tensile stress. If we move upward, and the specimen will endure compressive stress state, and this is called the compression testing. And this is the dimension for because this is a standard test, and we have standard dimension of the specimen, all the dimensions listed here, which means that if you want to make a standard test like this, you must make a standard material bar before the test, and then put it over here, and then start the test. And during the test, the load applied and the elongation that the material will be deformed are recording throughout the whole test. And then we will have some kind of stress strain curve on it. And I won't I should say that we will have the material test in a class, in a course called Materials Lab, maybe in your 2nd year or 3rd year. And at that time, I will explain to you in more detail about that. Okay. Now, with the test like this, what can we obtain? Okay, we can find out the modulus of elasticities, E, of that material. Sometimes, as you can see here, aka Young's modulus, and sometimes we call it Young's modulus. You may call it either the modulus of elasticity or Young's modulus. Each one is fine. And here is the law. It's something like the Hooke's law of a spring. For the spring, or even for the rubber band, and you have a relationship or a formula like this. The force equals to K times delta X, right? And K is the spring constant. F is an external force applied, and X is the elongation of the spring. And same analogy, for the material, we have sigma equals to capital E epsilon. The stress will be equal to the Young's modulus times the strain, which means that as long as we apply stress on a material, the material will exert or will deform to some distance of epsilon, the deformation, and the value of epsilon can be calculated by this equation, with a spring constant, or we should say the materials constant. We call it the modulus of elasticity, E, over here, which means that once the E is known, and then we can calculate epsilon from this law, elasticity, elastic modulus of elasticity law. We should say that, or sometimes we call it the Hooke's law of material. And E, how to calculate E? We can calculate E from the testing. That when we apply a force, we have sigma, and then we can calculate from a tensiometer, we can get an epsilon. And then when we increase the load to get another sigma 2, for example, and then we have another elongation or another strain, epsilon 2. And if we have 2 points, and then we can calculate the slope of the line, and the slope of the line is E, which means that as long as we have 2 test points, and then we can determine the elasticity of that material from the stress strain testing, or we call it the universal testing. And for most materials, it doesn't follow this, because as you can see here, that from here to here, it is tension. From here to here, since the sigma is negative, which means that it's compression. For some materials, it doesn't go along the same path. I mean, linearly. Sometimes it will go with another line, which means that the Young's modulus for elasticity or for compression might not be equal. I think time is almost up. Before we, all right. Before we dismiss, I will ask you a question. you think about what's the difference between modulus, constant, coefficient, or there's another one, parameters. We often hear about those terms. Sometimes we call some value is the modulus. For example, here, this is the modulus of elasticity. Sometimes we call a value a constant, and sometimes we call a value a coefficient, or sometimes we call it a value. We call a value which is a parameter. And what's the difference? So please think about that. Maybe next time when I recover from the COVID and we return to the classroom, and then maybe one of you can tell me the difference between these terms. What's the difference about that? We often hear about that, right? But we seldom think that what's the difference in between. Of course, I have to admit that for most people, we misuse one from another one. But however, strictly speaking, the definition has a little bit different from those among those terms. Okay, so it's 12 o'clock now. So is there any question about what I lectured today? Hello there. Are you still there? Oh my. Nobody there?
No question.
No question.
Yes, Asha, no question.
Okay, great. Thank you for your response. And if there's no question, as you can see here that I'm recording, so I will sorry. Yes, serious echoes, so I can hear you clearly. Okay, if you have any question, just write down here, and then I will answer your question. Anyone? Okay. I will answer your question next week. Okay. So same time is almost up. So I think here we finished all I lectured. Thank you for your thumbs up, and see you tomorrow. Not tomorrow. See you next time. Bye bye.
Bye.
Okay, you may leave the classroom here. Thank you. Bye. Okay. Some of you. Okay, so I will close the classroom. And if you have any other further question, just text me via line group. Thank you.
Can go back to sleep now, bro.
What are you saying, Bernardo? Hey,
Full auto.
say funny.
We have a class meeting.
Classmate.
Where's the pizza? You can come, I think, 12:30.
15.
It seems like everyone was online.
Then go
So they go to the pizza because everyone was online here.
Cleveland. Ito siya mga online dating. Ito ko ginawa ng TV na. Tuesday, do not leave.
What?
Yeah, you can leave now.
No, I'm waiting for you to leave first, man. No one in classroom. Hey, answer Mr. Chen, hey. Sudata.
Hey, Surata, please. Hey, Surata, please answer me the chain. They are coming.
We are coming.
Bro, Surata is not here. Where's Cleveland?
He's gone now. It's not painful, I mean. Hey, we are coming, hey. We're coming, hey.
Ah, yeah. Shy battery.
Utran ba phikano abashile nje bathi emaphisi abo bathi akazoom la.
Oh, c'est pour moi. Non, c'est slide mask. Son peu bleu. Okay.
Et c'est pour là.